Hello, my name is Koen Vervaeke. I'm the CEO of Magcam, and as a long-standing sponsor and exhibitor at the EDPC conference, it's my pleasure to deliver this presentation to you today. I would like to start out by thanking the exhibition and conference organizers for giving us the opportunity to still present our work. My presentation will cover the following topics. So after company introduction, I'll introduce our magnetic field camera technology and show how it is used to measure permanent magnet rotors with a focus on the magnetic field distribution of rotors and its analysis, including skewing angle measurements, Cohen torque analysis, and runout compensation. So Magcam is a technology leader in the field of permanent magnet inspection solutions. We have headquarters in Leuven, Belgium, and we are active in all industries that use high-end permanent magnets in their products in order to inspect these magnets. For this audience, the automotive industry is probably the most important one. So we have a global customer base of which you see a number of companies here. So our magnetic field camera technology is based on an integrated two-dimensional array of magnetic field sensors on one single chip. This ensures a high spatial resolution and a fast readout and very stable measurement system. I will not go into too much detail about this technology since it has been discussed elsewhere more elaborately. So this sensor chip is integrated into our Minicube 3D magnetic field camera, which measures magnetic field distributions of the three components of the magnetic field. So now we measure permanent magnet rotors, flat magnets, and magnet assemblies using this magnetic field camera. And for this, we integrate it into a scanner system. Our most versatile system is the Combi scanner, which can be used to measure both flat magnets and magnet assemblies and permanent magnet rotors. So for measuring permanent magnet rotors, you see a video here. The rotor is clamped in a rotary chuck mounted on a rotary table. The magnetic field camera is pointing sideways in the radial direction and will measure the surface of the rotor while it is rotating. So with this machine, you can easily swap between the flat measurement mode and the rotor measurement mode. It has an integrated laser sensor for runout compensation and for surface measurements. Here you see how the camera is moving upwards along the rotor surface in a continuous way. It can also be done in a band way, step by step, so there's two modes for that. In this machine, we can accommodate rotors with diameters ranging from 0 to 300 millimeters and an axial range of 250 millimeters. If you have larger or more heavy rotors, our dedicated rotor scanner is probably more suited, which can accommodate diameters up to 500 millimeters and lengths up to 450 millimeters. And after our camera has scanned the whole surface of the rotor, the image you see now is a typical resulting magnetic field distribution. So the whole system is controlled from our Magcam software, which you will see more in the next slides. So this is our dedicated rotor scanner that I already mentioned, which can accommodate larger rotors. Now, with our Magcam software, we can thoroughly analyze the measured magnetic field distributions in order to extract a whole lot of interesting parameters that characterize the quality of your permanent magnet rotor. So among those are the field distribution in 3 dimensions. So you have the axial, tangential, and radial magnetic field distributions at your disposal for analysis. From these distributions of the magnetic fields, we can extract the pole angles, both the size of the angle and also the peak values. We can measure pole skewing, to a Fourier analysis to look at higher harmonics, which can be relevant for example, noise issues in motors. Cohen torque analysis, which is also a very relevant topic in electric motors. And you can also compare these measured magnetic field distributions to computer simulations, which are based on the models that motor manufacturers have made in their design stage. So here I will show a number of examples how this analysis is performed. Here you see a permanent magnet rotor measurement with a surface permanent magnet system, and you see the three components of the magnetic field distribution as they are measured using the rotor scanner. Left is the radial field distribution, the middle shows tangential, and the rightmost image the axial distribution. You can make cross sections, look at the curves from the cross section. You can also integrate the field distributions and so on. Then we can go on to do a real poles analysis. A typical pole analysis would consist of either taking a cross section from the rotor or even integrating the whole axial range of the rotor measurement, and then looking at the one-dimensional curve, the line curve that results from that. On this curve, you can look at the local extreme values, which show the minima and maxima in your poles, as well as zero crossings, and from that derived the pole angles. And these give you already very interesting quality parameters for the rotor. You can also look at image statistics, both for the two-dimensional magnetic field distribution and the one-dimensional one. So it gives you, for example, the maximum of the field, the location of this maximum, same for the minimum, the mean field, and so on. Now an interesting parameter is skewing. So many rotors have a skew in their poles, and using the Magcam system and the Magcam software, you can in detail analyze this skewing angle of your rotor. How this is done is shown here. For a continuous skewed rotor, we take two cross sections at two different axial positions. For example, one near the bottom of the rotor, one near the top, and we make a cross sections resulting in two line plots. From the two line plots, we get automatically the zero crossings, as I've shown in the previous slide. Now you see that the zero crossings are shifted between these two axial positions, and the positions of the zero crossings are listed on the right side. So by taking the difference between each set of zero crossings from the bottom and the top, you get for every pole transition, you get a skewing angle. And because you know the distance in the axial direction, the actual distance between these two lines, you exactly can know the skewing angle per millimeter axial length of this rotor. Something similar can be done for a step-skewed rotor, as you can see here. So we take one cross-section line in the bottom segment of the rotor, one in the top segment, or if there are multiple segments, you can add as many lines as you want. And we repeat the same procedure as in the previous case, namely, we look at the cross sections, the zero crossings of these curves with the zero field position, and this is automatically detected and listed here. So by looking at the difference between each pair of pole transitions, you get the skewing angle actually for every pole transition. So you end up with a set of skewing angles on which you can also do statistics like the mean value, the standard deviation. So you know what variation you have within one rotor on the skewing angle. And as I said before, this can also be done for multiple stepped skews or V-shaped skewed rotors. So the possibilities are unlimited. Now, another very interesting feature for the rotor analysis is looking at the Fourier spectrum, which reveals higher harmonics in the rotor, in the magnetic field distribution of the rotor. And these harmonics play a role in, for example, the noise behavior of your electric motor. So if you have noise problems in a motor, this could be due to harmonics being present due to magnet issues in your rotor. So we have a cylindrically symmetric system here. So we can do a Fourier analysis and look at all the harmonics. For every axial position, we can actually calculate a spectrum. This is what you see on the top right. This gives these stripes because, of course, the harmonics are there along the whole length of the rotor. And then we can, for example, integrate these harmonics along the actual direction, and then we get one integrated spectrum of the rotor. And you can see on the bottom, and there you can automatically identify all the peaks. That means all the harmonics present in the rotor. So a very interesting feature now is that you can single out one specific harmonic and look at this harmonic as a function of the actual position on the rotor. So for that, you can just draw a vertical line here in the top right graph exactly on the desired harmonic and cut out this harmonic as a function of the actual position. And this gives these curves, as you can see on the left side. So each curve is the distribution of purely this harmonic as a function of the actual position on the rotor. This can give insight in exactly where on the rotor certain harmonics have the most contribution, for example. So, a next topic is cocking torque analysis. We can predict cocking torque from the Ampere rotor measurement, from a high-resolution rotor surface magnetic field distribution, and assuming a certain stator geometry that we need. Okay, so we just need to know the number of stator poles, the stator slot opening ratio, stator rotor air gap, and the axial length. And from there we can calculate a qualitative cocking torque curve and derive from that quantitative harmonics ratios, which is very interesting, and predict the cocking torque quality. So this allows you to predict cocking torque for the rotor so you don't have to put it in an actual stator to measure it, which is very interesting for discarding bad rotors before assembly. As an example, you see here a good rotor with a low cocking torque. The lower left image shows the two-dimensional field distribution. The top right or the top graph shows the integrated field distribution of the radial component of the field. And then the middle graph shows the calculated cocking torque curve. The curve as such doesn't really say much, but if we calculate the Fourier spectrum, you see the bottom graph, which shows one dominant harmonic, as is expected, actually. So then we look at a bad rotor, and you will see that on the level of the pure direct magnetic field distribution, you don't really see much by the naked eye. But if we do the cocking torque analysis, we see that we get a completely different curve out of it. And looking at the harmonics contents, you see lower harmonics popping up, which become dominant, even larger than the harmonic which was dominant previously. So that base harmonic has not changed, basically, but the others have become much larger and dominant. And this is quite striking, because from the naked eye, you typically don't see anything, or you would think that you don't see anything, but these data are hidden. This information is hidden in the data. And we have these nice algorithms to extract them from the data, make them visible, and actually use them as a pass-fail or a quality measurement tool. Okay, so as a next topic, we can look at a rotor runout compensation, for which we use our laser sensor. So we have a laser equipped on the rotor scanner and the combi scanner, and with that you can actually measure the diameter of the rotor, the whole surface, and also the runout. You can do full surface scanning as well. So the runout compensation works like this. We measure the runout on the shafts of the rotor, typically, or on the body, as you wish, and then we can compensate for this runout during the actual measurement. This way we can get rid of the residual runouts due to the clamping tolerances in our chuck, or due to the wobble, because at higher actual positions you have a bit more runout than at the bottom. And typically you could have a residual runout of less than 10 micron at the bottom of the clamping and 20 micron at the top. And using this runout compensation, you can get it down to 1 micron on both sides. So this is an image of what the result could look like. On the left side, you see an uncompensated measurement. You see on the bottom, it's quite okay, but on the top, you see a first harmonic content. The bottom graph shows a line near the top of the rotor. Then after compensation, using the method I just described, you see the right graph, and you see this first harmonic has just disappeared from the top of the rotor. The bottom has not changed much. Then we can also look at the effect of this runout on the magnetic fields that we measure. So an uncompensated measurement with a runout at the top of the rotor will show, you can see that you actually get the shape of the runout reproduced in the magnetic measurement. So you see that there's an influence of that. And after compensation, you can see that this first harmonic has disappeared from the magnetic measurement as well, and also from the laser measurement. We still see a second harmonic in there. The second harmonic has more to do with the elliptically shaped rotor, so it's not hasn't anything to do with the actual clamping of the rotor. It's intrinsic of the rotor. And we even see a little bit of that influence in the magnetic field measurements. So it shows that we can really correlate the magnetic field measurement and the topographic measurements together and see what is the cause, for example, of certain magnetic issues. Like here, it is purely due to the shape of the rotor. Okay, so now I've shown a number of options or possibilities using our scanners, our technology for measuring and analyzing permanent magnet rotors. Here are some collaboration options how Magcam can help you with your permanent magnet or permanent magnet rotor application. So we do perform service measurements. So we analyze your samples, your rotors at our lab, and you get a full report and analysis made by our experts. Of course, you have the option to purchase our devices so you can benefit from them in-house and use them to measure all your magnets and rotors in-house, and also deepen your own expertise and understanding in your own magnetic products. And we also do development projects when some customization is needed, for example, in software or in hardware, or for integration of our systems in production lines. Now, as a conclusion, I've shown you our magnetic field camera technology, which is high speed, high accuracy, measurements of permanent magnetic field distributions, our advanced data analysis software, which is one of our main differentiators also in the market, which can be used for R&D, quality control, or production environments. Then I've shown you how permanent magnet rotors can be measured using our systems. We have a combi scanner and a rotor scanner, which can be used for that. And I've shown you in some applications, in some examples, analysis of permanent magnet rotors, including poles, amplitude, and angles, skewing of the poles, fast Fourier transform results, Cohen torque analysis, runout compensation, and laser topography measurements. So that brings me to the end of my presentation. I want to thank you very much, and I'd like to invite you to check out our virtual booth and also check out our online social media. Thank you very much.